Good evening, everyone. My name is Chris, and I'm a theoretical particle physicist, but my particles that I will be talking about are much, much smaller than Zafir was just talking about. So today I will take you on a little journey to the smallest scales and the biggest questions. So whenever we do physics, we have a very important assumption in the back of our mind, and that is that any law that we observe here and now in our laboratory should still be valid anywhere in the universe and at any time. Now, if that assumption is true, that means that by studying the laws of the most fundamental building blocks of nature, we can learn something about the entire universe and about its history, including our own history. So I hope that is enough motivation to study those particles. But when I talk about fundamental particles, what do I actually mean? Let's start with a glass of water and then zoom in step by step. So I remind you, water consists of H2O molecules, and you will guess it, H2O molecules are not elementary particles. They consist of hydrogen and oxygen. Let's just focus on a single hydrogen atom. It's the smallest atom you can think of. It's just one proton and one electron. But again, it's not an elementary particle because it has precisely this substructure. So let's go now a step deeper, just focus on the proton. What many people don't realize is how much smaller a proton is. It's just like a grain of rice in a football stadium. The rest is just empty space. And again, from this picture you see that we particle physicists believe that a proton is not an elementary particle either. It has, again, a substructure. We call these substructure quarks and gluons. Or the gluons, they act like glue, which keep everything confined within a proton radius. And now you might ask, what happens if we zoom into a single quark or gluon? Do they have a substructure? Well, something surprising happens. When we look closer to what a quark or gluon consists of, we see that it consists of more quarks and gluons. That means we don't see something new, we just see more of the same. And that is why we call quarks and gluons elementary particles. But how did we figure all that out? I mean, it's so incredibly small, unimaginably small. Usually the way of choice, or the method of choice, is using a collider, just smashing the things into each other. So this is the Large Hadron Collider. It's the latest and greatest toy in particle physics. It's a 27-kilometer ring, 100 meters below the Earth. And the way it basically works is that you take a bunch of protons, we accelerate them in this ring, we take another bunch of protons, accelerate in the opposite direction, and then we collide them in one of the detectors. So this is the Atlas detector. Itself is the size of a 5-story building. You see people working down there. It's a really humbling machine. And one important thing that, about these collisions is that we cannot study the collision itself, because all the interesting action happens within a proton radius, and we just cannot build a detector that small. So all we can do is study the debris. And I told you before that a proton, from a particle physics standpoint, is a very complicated object. It's like a trash bag full of stuff. And this is more or less what you would expect when you throw two trash bags into each other. You get a lot of mess. So that's the experimental side. And now, just collecting data doesn't help you. You have to make sense out of it. Otherwise, you don't learn anything. And that's where I'm coming in. But before I go into that, there's one important remark, is that we can never predict the outcome of one specific collision event. All we can predict and test is the outcome of many collision events in the following sense. Imagine you're in a casino and you want to find out whether or not the dice are loaded. Throwing them once won't tell you anything, it's just a number. But you throw it many times, you can put each result into a histogram like this. This would correspond to colliding many protons with each other and recording all the data. Now we need a theory. So let's assume we have good faith in the casino and we believe that the dice are fair. So then we can take this assumption, we can translate it into a computer code and let the computer simulate the consequences of that theory. That's essentially what I do. I take our current best understanding of how particles work, translate it into computer code and let it simulate. And in the last step, we compare our expectation with our observation, and we see whether or not they agree. In this case, we would conclude they don't agree, and therefore the theory is wrong, as in the assumption that the dice are fair is not true. Now we have done exactly this for the past couple of decades, this basic idea, and we have come up with a model, the so-called standard model of particle physics, which passes all the experimental tests that we put it up to. And you can picture this model as like a periodic table of elementary particles. Before I talked a little bit about the electron and about quarks and gluons, which make up the protons and neutrons, and there are many other particles that we usually don't hear so much about. However, we're not really happy with this model. For one, it's really complicated, and we don't really like the idea that nature at its very fundamental level is that complicated mess. But not only that, one important feature of this model is that it doesn't include gravity. It doesn't talk at all about this. One reason is that we cannot measure gravitational effects in a collider. But not only that, when we try to combine a theory of gravity with the theory of particle interactions, we see that the two are incompatible. So clearly, we are not there yet. We have still a long way to go. If we want to answer all the big questions about the universe and how everything is connected, we have to understand its basic building blocks. I'm Chris, and I help to demystify some of those mysteries. Thank you very much.